Example M7.2. Draw the shear force and bending moment diagrams for the simply supported beam shown. So here, unlike the previous example, we have a concentrated moment instead of a concentrated load. And interestingly enough, this will affect the direction of the reactions at A and C. All right. Now, if we imagine the beam, okay, subjected to this concentrated moment, then we would, by intuition, we would know that this would cause a bending in this manner. Okay, a bending of the deflection of the beam in this manner. Therefore, this is being raised up, and I assume that this is going down, and this would be going up. Okay, so this will help you also with your initial assumptions of the directions of the reactions. So we can check if indeed these initial assumptions are correct. Okay, by first drawing out the free body diagram of the beam and then solving for the reaction forces at A and C. Okay, so here we sum up moments about A and apply the equilibrium condition. Therefore, Cy is equal to MO or M naught over L. Okay, and summing up vertical forces, we see that AY is M naught over L going downwards. All right, so that is basically validating our assumption that RA is going down. Okay, so there we have CY and AY. Next, we have the free body diagrams for the shear and moment functions. All right, so for segment AB, we pass a section here, okay, at A, and then we pass a section here at B. Okay, so as to expose the internal shear and moment, internal shear force and internal bending moment. Okay, or internal resisting moment rather. All right, so for the shear function for segment AB, we find that by summing up vertical forces, we have a shear internal shear force of negative M naught over L. Okay, and then the moment function, by taking by summing up moments about A, taking counterclockwise to be positive, and then applying the equilibrium condition, the internal bending moment is negative M naught over L times X, and therefore this is linear, okay, with respect to X, and we see that the slope is going downwards. All right, so to draw out the shear and the moment diagram for segment AB, here that's negative, therefore for this segment here, it should be in this form. So it goes down here, and then let me use that line function again, make things easier. Okay, so this is negative M naught over L. Okay, that next we have negative M naught over L times X, and therefore that is a straight line here. Okay, straight line going down here. So that is M naught over negative M naught over L, and therefore this is negative M naught over L times X, right? Times X. So X at that point is L over 2 times L over 2. You cancel out L. You will end up with M naught over 2. Okay. So next, segment BC, we have to include the concentrated moment at this point in time already in our analysis. So summing up vertical forces, we see that there is no change from the shear function of segment AB and segment BC, because there is no additional load applied. There's only a concentrated moment. Okay. Next, the moment function will definitely be affected. All right. So, summing up moments about BB, this is supposed to be BB, and applying the equilibrium condition to define the bending moment function, we have m naught, okay, over Lx. So this produces a counterclockwise moment, minus m naught, okay, so this produces a clockwise moment, that's negative, plus m equals 0. And you will end up with m naught minus m naught over Lx, okay. So then we can draw out the shear and the moment diagram of segment BC. So since it is constant at negative m naught over L for the shear diagram, then we just continue this line here. Okay, maybe I'll just continue that line. Okay. And then close that off. Okay. Take note also, this goes up and terminates 0 because there is it goes up with the addition of this reaction force at C. Alright, we talked about that in the previous example, that a concentrated load will warrant a jump or discontinuity at the point where the concentrated load is located by a magnitude equal to the magnitude of the concentrated load. Okay, so therefore that goes up by m naught over L. Okay, terminating at 0. While here, okay, we have m naught minus m naught over L times x. Okay, so here we have m naught. We'll see what point it is on the moment diagram also. Okay, so at L over 2, at x equals L over 2, your m is equal to m naught minus m naught over L times L over 2. Okay, so this will be equal to m naught plus m naught over 2, minus rather, okay, minus m naught over 2. This will cancel out, and therefore this is positive m naught over 2. Okay, so instead of being here, your moment diagram will continue at this point here. Okay, at this point here of m naught over 2. Now what do we notice? We notice that the length here from here to here is m naught, right? Because this is m naught over 2 and this is m naught over 2. And it follows that when there is a concentrated load or concentrated moment rather, the moment diagram, the presence of the concentrated moment will cause a discontinuity or a jump at the point of the application of the concentrated moment in the moment diagram. Okay, so we can finish this off by connecting the 2 points. Okay, and therefore you have the shear and moment diagram of this beam right here. Okay, so the maximum moment, okay, this is the maximum shear diagram, the maximum value for shear, okay, Vmax, and the maximum value for the moment is positive negative m naught over 2, okay, which is shown here. Okay, and this is a better or a neater representation of the shear and moment diagram. So I hope that's clear. In the next video, we'll be talking about how to graphically a graphical method rather for drawing out the shear and moment diagram, because imagine if there are more than one concentrated moments along the path, then along the beam rather, then that would warrant a number of different different cutting planes, which would warrant a number of different shear functions and moment functions. So to make the process easier, we'll be talking about a graphical method in the next video.